So let's get started. So remember, this chapter is going to be all about alkyl halides and the reactions of alkyl halides. We said that they're going to undergo two different types of reactions here: substitution reactions and elimination reactions. And last class, all we did was talk about the substitution reactions, right, and being able to predict products. So let's just review real quick. Here are these substitution reactions here, and you're going to give me the products of these reactions. All right, so let's go through this first one together, and then I'm going to give you another minute to do the second one here. So first of all, terminology that we learned is in these reactions we have what's called a nucleophile, the thing that really wants the nucleus, the electrophile, the thing that really wants electrons, right? And our nucleophile and electrophile are going to react with one another. And then we have a leaving group, something that's being kicked off, okay? So what is the leaving group in my first set of reactants here? The chlorine, right? That's what's going to get kicked off. What's the nucleophile? The thing on the right or the thing on the left? The thing on the right, right? So our nucleophile is what has a lot of electrons, right? That's why it wants the nucleus. So a typical feature of a nucleophile is that negative charge. They also always have lone pairs. So I didn't put these in here, right? But my nucleophile, this sulfur, has these lone pairs. So they have a bunch of electrons. That's what it means to be a nucleophile. So in this case, this is my nucleophile. And what's going to be my electrophile in this reaction?
Carbon.
The carbon at the base of the halogen, right? So that's what I'm going to have a new bond between. My nucleophile, in particular the sulfur with its negative charge, and my electrophile, that carbon. And in this process, I'm going to kick off that leaving group, okay? So in this case here, I would start by redrawing all those carbons in my electrophile. That's the carbon where I'm going to have my new bond. to my nucleophile, the sulfur, and I gotta make sure to include the 3 carbons on the back end of that. All right, I should have the same number of carbons on both sides. Okay, this was a, because that sulfur has a negative charge, we kind of broke these into these 2 categories. This would be a negatively charged nucleophile. Or again, that negative charge is just being replaced with a new bond. All right, so this pair of electrons here is actually what makes up my new bond over here. Okay, that's where that negative charge goes, becomes a bond. And then the other one that we talked about were neutral nucleophiles. Okay, so again, let's go through that same process. What's my leaving group? The bromine. What's my electrophile? That carbon at the base of the bromine. All right, so then this thing over here is my nucleophile, but in particular, which atom in this nucleophile is going to have that new bond? It's going to be the oxygen, actually. I'm going to lose a hydrogen in this process, right? Hydrogen can only have that one bond. So in this case, that electron-rich species with its lone pairs is this oxygen. So with our neutral nucleophiles, we're going to lose a hydrogen. And replace with our new electrophile nucleophile bond. So everybody take a second and see if you can't give me that product. All right, and so visually, let me just try to hammer something home as exactly what's happening here. I'm going to kind of explicitly draw out this oxygen-hydrogen bond. Just kind of draw it as a bond here. Because again, what's happening is I'm going to be losing that hydrogen and now kind of picking this up and making a new bond with that electrophilic carbon. Right, so my bromine goes away, and now I have a new bond forming over here, right? That's what my new bond is going to be between the oxygen in my nucleophile and that electrophilic carbon. Yeah, whatever. Okay, and similar to what we saw last chapter, we're adding more carbons, right? So that's what's going to make these reactions kind of at least like pain in the butt, maybe just intimidating, is that we get these big ugly products on the other side, right? We're actually growing our carbon chain, growing our molecule. So there's just a little bit more stuff to keep track of. I think it doesn't really make it that much harder, but it does make it more intimidating, right? It makes it, when you look at it, you're like, oh my God, I have no idea what's going on here, right? But when you pick it apart and sort of look at the process, It's going to be the same for both of these here. Again, for the neutral one, it's just going to lose a hydrogen. Importantly, though, these are exam questions, right? This is exactly what I would put on an exam, is here's this substrate, here's this reactant, or rather, here's this reagent, draw me the substitution product. Right? At the very beginning of the semester, we talked about how this course was a lot different than like a Chem 3A or a Chem 1A, 1B course, in that we're not doing any math in here, right? But it is very structure-based. It's all about being able to draw the structures, the products of these reactions, okay? So again, this would be an exact sort of exam question here. Put these two things together and say, draw me the product. All right, so just to be clear. All right. Again, we sort of have these two reactions that are in competition with one another, but we've only really talked about this one here, right? The substitution reaction. We haven't talked about the competition. We haven't talked about the elimination reactions yet. We're just kind of sticking with substitution for right now and making sure that we can draw these products. All right. Now, our substitution reactions. We're going to throw them into two different bins here. The first one is called an SN1 reaction. And the other one is called an SN2 reaction. All right. So I'm actually going to focus on the SN2 ones first. All right, let's just put down an example. Here's my alkyl halide. But I'm going to stick this bromine on this wedged bond here. All right, so it's sticking out at the page at U. I'm going to react it with a hydroxide ion. Okay, actually, if I just make this a normal bond, let's start there. Everybody take a second and predict me the product. All right, so my new bond is going to be between this electrophilic carbon right here and which atom in my nucleophile? The oxygen. Awesome. All right, but now, if I tell you that this reaction is an SN2 reaction, so what does that mean? So these reactions occur from what's called a backside attack. All right, so if I had this bond with my bromine and I knew that it was actually sticking out of the page, it was a wedged bond here. Right, remember wedge means that it's sticking out at you. The hydroxide ion, when it reacts with that electrophilic carbon, it has to approach it from the opposite side of where that bromine is. It's going to come around the back side and attack that carbon. All right, so a backside attack. meaning it attacks from the opposite direction. We can say our nucleophile attacks, they use some violent words here in organic chemistry. I don't know, but that's what it's called, a nucleophilic attack. The electrophile from the opposite direction of our leaving group. Okay, so if our bromine's sticking out at you, that means that the hydroxide is coming from the opposite side. All right, importantly, this leads to a stereochem inversion. And inversion is kind of a key word here, because what we're going to see is if we properly draw our product, we have to draw that new bond, that new hydroxide carbon bond, in the opposite direction of where my leaving group bond was. So my leaving group was sticking out of the page. My hydroxide ion with its backside attack is now pointing into the page. Okay? This is a stereochemical inversion. All right, and the bottom line with our stereochemical inversion is that a wedge becomes a dash, or a dash becomes a wedge.
Why did you get rid of the H on this one?
Because it has a negative charge, right? If it was neutral, if it was water, so I could do this same reaction with water, and I would have the same product, but I would lose a hydrogen because it's a neutral nucleophile, right? This one's already got a negative charge. It's a good question. All right, so before we move on, let's just practice this for a second. I'm going to tell you all that the following reactions are SN2 reactions, and you're going to draw me my products here with our proper stereochemistry. Okay, so let's just pick that same example we did at the beginning, but this time I'm going to tell you that that chlorine is on a wedged bond, reacting it with that sulfur nucleophile, sulfide. So for this one, this was one of the examples we did at the beginning of class, right? I'm going to have a new bond between my sulfur and that electrophilic carbon. All right, the big difference is now we learn that this is an SN2 reaction, and so there's going to be an inversion in my stereochemistry where that wedged bond where that dashed bond becomes a wedged bond. All right, so again, here we see this dash. Becomes this wedge. All right, I flipped my stereochem. All right, same thing down here. I have a new bond between my electrophilic carbon and this negatively charged oxygen in my nucleophile. All right, and then what's going to happen to this wedge bond here? It's going to become a dash. So I'm going to draw in my new bond. All right, I'm going to draw my carbons from my 1, 2, 3, 4, 5, 6 carbons. All right. Now I'm going to add in that new bond between my electrophile, which was this, and that oxygen on my nucleophile. Boom, there's my new bond. But again, I'm going to remember to invert my stereochemistry, so this is going to be a dashed bond. All right, I still got to include all the back half of this molecule here, so I'm going to put in that there. Real quick, what do we call this thing? Carbonyl. Yep, the carbon-oxygen double bond is a carbonyl. Okay, but again, importantly, I have my substitution reaction, and again, what we just learned is for an SN2, we got to flip our stereochemistry. Going down to this example here, now I have these two different types of bonds, right? I got this methyl group over here on a wedge and an iodo group over here on a dash. Importantly, my electrophile is where?
Is it going to be on the iodo group?
On the base of the halogen, right? So on the base of that iodo group, that's where my new bond is going to be formed. And that is the only carbon that's going to be inverted, right? So we're not going to see any change in this group here because there's quite simply no reaction occurring over there. But this carbon right here, formerly my electrophile, is now going to have a wedged bond. It's going to turn from a dash to a wedge, and I'm going to attach that oxygen. Right, so again, let's make note, we only have inversion at our electrophile, at our electrophilic carbon. All right, the inversion occurs because of that nucleophile attacking from the opposite side. There's nothing going on over here. Right? That methyl group isn't doing anything. It's not reacting at all. There's no such change going on over there. All right, so those are SN2 reactions where we have this inversion in our stereochemistry. And that's really the word that I want you to have synonymous with those SN2 is inversion. We got to flip our stereochemistry. All right, SN1 reactions. So these really, the names really pertain to the mechanisms of the reaction, but we don't really do mechanisms in this course, so we're kind of just like doing a little bit like more broad picture of what the outcome is of these here. Okay, our SN1 reactions, they go through a carbocation intermediate. And kind of the bottom line is that there is no inversion that occurs. No stereochemistry inversion with an SN1 reaction. All right. Instead, you got to draw both products. Okay, so what do I mean by that? Let's look at a specific example. Again, we're always starting with our alkyl halide. I'm going to react it with some nucleophile. In this case, I'm going to use this neutral nucleophile here. Okay. When I draw my products, if this was an SN2, I'd flip my dashes and my wedges, right? Here, I'm going to have to actually draw both products. So again, I'm creating that new bond between my electrophilic carbon and my nucleophile. Specifically, which atom in this nucleophile? The sulfur, yep. Okay, but I'm going to have to include both a product where that sulfur is on this dash, but then also include a second product where it's on the wedge, where I do flip. All right, so in this second product, I'm going to flip my dashes to wedges.
Do you have to show that they change like that, or would it be different if you would have known there?
It's a good idea to do it. So in this particular example, if you moved the sulfur over here, it would be equivalent because they're both methyl, but that's not always going to be the case.
Okay.
Right? So get in the habit of flipping them. Right? So what we're going to do for our SN1 reaction is draw two products. One with no flip and one with the flip. All right, so again, I'm going to tell you that these reactions are SN1 reactions. right, so for this first one, let me make myself some more room here. Because since this is an SN1 reaction, I'm going to have to draw two products. All right, so one of them where I don't do anything to these dashes and wedges, I'm just going to replace that chlorine with my nucleophile, my oxygen. All right, but then I'm going to draw a second product where I'm going to change my wedge and my dash, right? So now this one up top will be the dash, and this one down at the bottom will be the wedge. These are my two products for this reaction. All right, we got to draw them both for an SN1 reaction. Oh, that's not what I want to do. Okay, so now this one here, to be clear, this might look weird. This right here is an ethyl group. There's a carbon here and a carbon here. Okay, we only draw the one sticking out with the little dash. The other one gets a normal just line. But yes, I know that this looks weird, but this is an ethyl group right here. That's how we would draw an ethyl group. All right, so I'm going to do my first product where I don't change anything around. I'm just going to redraw. Boom, boom, boom. Wedge over here. Dash over here with that ethyl group. And then what am I substituting that bromine for? What's my new functional group over here? Just OH, right? I'm going to lose a hydrogen from this neutral nucleophile. Boom. And then I'm going to draw the same thing, but this time I'm going to flip my dash and my wedge. Right? So this wedge becomes a dash, that dash becomes a wedge. Boom. All right, let me just move this. I feel like I'm going to run out of room. Okay, so again, I'm going to draw my product here where I don't change anything. I'll put it below since I drew this mega huge for no good reason. All right, and I'm going to replace that leaving group with what functional group over here? NH2. Awesome. Losing a hydrogen. All right, and then I'm going to draw a second product. All right, but importantly, just like we discussed last time, the only thing I'm going to flip is going to be about that electrophilic site, right? So I don't just change everything. I'm only going to change the ones about that electrophile. So in this case, it's only this carbon where I'm going to change my dash to a wedge and my wedge to a dash. This one over here is not involved in the reaction at all, so it just stays the same. All right, but I get a mixture of these two products here.
For some reason, I thought on the other one, on the second example, that the ethyl group would follow the change as well.
It does, in the sense that it was a wedge and now it's a dash, or you draw both of them.
Yeah.
Okay, and that's because it's on that electrophile, right? That ethyl group was attached to that electrophile, which is why it gets switched. Unlike our third example, where this one over here doesn't get switched because it's not attached to an electrophile.
In that last one, would it also not be written as OH because it started off as a water product?
It's written as OH because it's neutral, so it loses a hydrogen.
But like how you have it written is as HO?
Oh, that doesn't matter.
Okay.
You could write it as OH. I mean, it's really just like what's more convenient. It's important that the oxygen is what's attached to that carbon. So you could write it with the hydrogen over here, and it's the exact same thing.
Just as long as it loses that other hydrogen.
Yeah, as long as you don't say something like OH, where it's the hydrogen on the other end of that bond, that one wouldn't be correct, right? It has to be the oxygen that's attached. But yeah, HO, OH, they're the same thing, just what's kind of more convenient, I had more space on this side, so I wrote it as HO. Okay, but yes, this would be equivalent if I moved my hydrogen over here as well. That's perfectly fine.
And then, last example, if we had another iodine constant, and a slashed, like, on the other side with the wedge.
Like over here?
Yeah, if we had,
Yeah, we're not going to have like multiple sites. You would, in this case, then you would have to like worry about all that, and you would get this mixture of actually 4 different things. It would be kind of a nightmare, right? But we're only going to ever have one site that's being reacted. All right, so our next step will be to introduce these. Now, the other side of this, the elimination, but rather than spend these last 8 minutes trying to cram that in, let's just practice this crap again, all right? Again, drawing these products, I understand that this is not like a very easy thing. It's going to come with practice. It takes like a certain eye to be able to see what's going on, right? But again, it's one of those practice makes perfect kind of things. So it's one of those things where if you're doing your homework and you get it right sometimes and wrong other times, you don't want to be like, okay, finally I got my 4, I'm just going to move on with my life. Make sure that you really are understanding how you're putting these pieces together, right? It's kind of more like a little bit of a puzzle than it is a math problem, which is what chemistry is at the Chem 3A level. All right, so for these ones, I'm going to tell you that these are SN2 reactions. Actually, let's do. right, so remember that SN2 means that there's going to be that inversion. All right, so again, when you hear SN2, you think inversion, which means I'm going to swap my wedge, or my dash rather, for a wedge. All right, and since this was a neutral nucleophile, I'm going to need to remove a hydrogen from that sulfur. All right, again, this is an SN2, so I'm going to invert about that electrophile, change this wedge to a dash. But now this was this negatively charged nucleophile, so I don't lose any hydrogens. I just replace that negative charge with that new bond. All right, and then SN1, kind of even more of a pain in the butt, because I can't just include one product, I gotta include two of them. The first one, I'm not gonna change anything, I'm just gonna swap out my leaving group for my nucleophile. Importantly, counting carbons, right, I have 1, 2 carbons, so I'm gonna have to put 1, 2 carbons on the other end of that oxygen. If they were pointed in a different direction, that's fine, right, as long as you have 2 carbons on that oxygen. And importantly, the oxygen is what's attached to that electrophile, right? It can't be a carbon, it has to be the oxygen. And then for my other one, all right, I'm also gonna have that same new functional group, but then I'm gonna switch my wedge and my dash. So this bond over here is gonna become the dash. This bond over here is what will become my wedge. All right, I got to include both of these products because this is an SN1 reaction. Okay? Cool. All right, we'll leave it at that. I will say this is definitely the most challenging.